Section 6.3 is on linear programming. So basically what we're going to do in this chapter is, or this section, is we're going to solve optimization problems. And what optimization problems are problems which involve finding the greatest, also called the maximum, or the least, the minimum, value of a function. So a function, as you know, could be something like, I don't know, f equals 3x minus 2y. And what these questions involved is, what would make this f amount, what would make it as big as possible? Like what value of x and what value of y would there be so that this f value is as big as possible? So if you think of it, probably what you'd have to do in this case is make the x really, really, really big and make the y really, really, really small. Why would you make the y really, really small? Because you are taking away this amount. You don't want to take away very much. That would give you the maximum amount. If you want to get the minimum amount, do the opposite. Make x really, really small and make y really, really big. Okay, so that gives you a sense of what we're doing with optimization problems. Linear programming is the method used to solve optimization problems. So if we want to solve an optimization problem, we use a process called linear programming. All right, with linear programming, there's two pieces to it. There's the objective function, which is what we want to maximize or minimize. So this is, as I said, really common in business and government and stuff. Like, what are some things that people try to maximize in business? Come on now, you can get this one. What do people try to maximize in business? They try to maximize profit. They want money, right? So that's one thing. That could be the objective function, is the money that you're earning, the profit. Maybe what you're trying to maximize is the number of shirts that you're producing every day. You're a shirt producer and you want to make lots of shirts, so you're maximizing that. What's some things that you could be minimizing? Well, you want to minimize costs, right? You don't want to be spending thousands and thousands of dollars on material for your shirts. You want to spend as little as possible, probably. Maybe what you want to minimize is the hours worked by your workers, because more hours worked equals more money out to the workers. So there's all these things that you want to maximize and minimize. And if you come up with a function that kind of summarizes those factors, you have the objective function. Okay, a little complicated to talk about, but once we get to example, I think you'll see what I mean. Okay, system of constraints. If something's a constraint on you, what does that mean? Kind of means like it holds you back, right? Say that I was trying to maximize profit. And the way I get profit is that I sell pencils for $2 a pencil, and I also sell pens for $3 a pen. Then we'll get kind of more into this later, but the formula for profit would be 2 times x, because x is the number of pencils I sell. If I sold 100 pencils, that'd be 2 times 100. If I sold 1,000 pencils, that'd be 2 times 1,000. And we also have this plus 3y, where y is the number of pens. If I sold 20 pens, it'd be 3 times 20. If I sold 100,000 pens, it'd be 3 times 100,000. Now, if I want to maximize my profits, you'd probably look at me and say, well, that's very, very easy. Just make x, the number of pens I sold, make that really, really big, like as big as possible. I'm talking millions and billions if possible. Probably not billions of pencils, but maybe millions as possible. Pencils. And pens as well. Make that really, really big. Okay, finished. Just make those really big and the job's done. But we have to consider these constraints. Constraints are things that hold us back. So if we're trying to maximize profit from our pencils and our pens, what are some of the things that are going to hold us back? Like, we can't produce billions and billions of pens, can we? Why not? Well, because there's only a certain amount of time every day that we have to make pencils. There's only a certain amount of money we have to buy the materials for the pencils. There's only a certain number of hours that workers can come to work. All these things are constraints. And that's why the solution, the maximum output for our pencil and pens, is probably not going to be numbers like millions and billions and stuff like that. Maybe it's only numbers like making 10,000 pencils in a day or 3,000. I don't know. It depends on the constraints. The system of constraints are the things that kind of hold us back, and they're linear inequalities. Remember, that's what we graphed last time when we had the half planes being graphed and stuff. Linear inequalities whose solution is called the feasible solution. So if something's feasible, it's like it's possible. It's imaginable. So with my pencil and pens example, chances are that 10 billion pens doesn't fit in the feasible solution, because it's just too much money to get all those pens and too many man hours to make all those pens and all that kind of stuff. the steps to solve these. This is also going to seem a bit obscure till we get to an example. Step 1, you're going to sketch the region determined by the system of constraints. So these constraints we talked about here, you're going to graph the system. It's a system of linear inequalities just like we did last day. So what you're going to have is, this is my graph, and you're going to end up graphing a system of constraints. And maybe it's going to be something like this. Maybe, I don't know what we're even talking about here, but maybe one of the inequalities is here, and whoops, that should be a straight line. And let's say one of the inequalities is right along the x-axis. That often happens. And let's say the other one is here. I'm just completely making this up. And when we do all the shading and everything, let's say the region that's shaded is in here. This is my feasible region. Now, here's the cool thing about these questions, these optimization problems, is that the only place where a true maximum or minimum could be are at the vertices of the shaded area. You know what a vertex is? It's like a point, right? So if I draw any shape, any closed polygon like this, the vertices are the points, like 1, 2, 3, 4, 5. Those are all vertices. Triangle, 3 vertices. Square, 4 vertices, right? Well, it turns out that in optimization problems, the maximum or minimum is always, every single time, not going to be in this shaded region. It's going to be at the vertices of the shaded region. That's kind of cool. So what you want to do is you want to find the vertices of the region. So we'd figure out all these points. Well, looks like this one's 0, 0. And this one up here, I don't know, I'm just making this up, right? Let's just say this is 3, 8. I'm just making that up. And let's say this point out here is 7, 0 or something. Okay, that would be step 2. Just find the different vertices. Step 3 would be calculate the value of the objective function at each vertex. So if our objective function is something like profit equals, I can't remember what I said was before, was it like 2x plus 3y or something like that? I think that's what it was with my pens and pencils. Then what I would do is I would plug, for each of these 3 points, I'd get a value for the profit. So for example, if I plug this 0 and this 0 in here, 0, 0, well, that'd mean making no pens and no pencils. In other words, my profit would be 0. Well, that's probably going to be the minimum. We can't do much worse than that. Okay, if I put 7 and 0, that would mean I'd make 7 pencils and no pens. I'd have 2 times 7 is 14 plus 0, so I'd have 14. Okay, my profit would be $14. I know these don't make really much sense. It's just an example I'm using. And if I did this one, 2 times 3 is 6. I better write that down, I'm going to forget. 3 times 8 is 24, and if I add those together, I get 30. The profit is 30. Okay, thank goodness that mathematicians have figured out that the maximum and minimum are always going to be in one of those vertices. You don't need to try all these points inside here, the shaded ones. They are definitely, absolutely, positively going to be between 0, which is our minimum. That's the worst you can do. If you make no pens and pencils, you make no money. And 30 is the most you can make. And how do you make that much? If you make 3 pencils and 8 pens, then you would know that you'd have your profit of 30. And I hope you realize that's like really, really, really useful information for a business to be able to figure out what's the optimal number of product I should make. You don't want to just be guessing and saying, I think it's probably best if we make 10 pencils and 22 pens. And then if you do the math 10 years later, you figure out, wow, we were actually only making half the money we could have made. That would be bad news. So last step, I think I already alluded to it, you calculate the value of each one like we did, and then you figure out what's the maximum and the minimum value. Well, in this case, it's pretty easy to see that the maximum is up here, my maximum is 30, and then the minimum is down here, it's at 0. You don't need to even try any of these points. Okay, that's the step. Let's see if we can work through one example together. It says, now next class what we're going to do, first of all, just to see where we're headed here, next class what we're going to do is we're going to do exactly the same thing, but they're all going to be word problems, and you got to figure out the objective function, and you got to figure out the constraints. I'm sure you're all going to look forward to that. You love those word problems. But today, to kind of ease you into it a little bit, they just give you the objective function. So the objective function in this case is c equals 7x plus 3y. So do you remember what this means? This is the thing that you're trying to maximize or minimize. And in this case, it's asking us to find both. It says find the maximum. It also says find the minimum. So this is what we want to get as big as possible. We want to see what value should I plug in there to x and in there for y to make this as big as possible, and also what into x and y to make it as small as possible. Okay, if that was all the information we had, it would be obvious. Make x enormously big, like billions and billions and trillions, and make this billions and billions and trillions, and that would be as big as possible. If you want it as a minimum, make x as small as possible and y as possible, and we got a minimum. But we have constraints. Here's the constraints right here. Okay, so let's go back, look at our step. Step 1 says, sketch the region determined by the system of constraints. So we have to do just like what we did last time. We have to graph these system of inequalities just like we did last class. Now, before you go any further, I want you to look at the last two here, these two here. This happens a lot. It says x is greater than or equal to 0, y is greater than or equal to 0. In other words, x and y cannot be what kind of number? If they're greater than or equal to 0, they cannot be negative. Now this is really common in these questions. Why is it common? Because remember my question with the pens, or my example with the pens and pencils. Is it at all possible to have a negative number of pencils? No. Is it possible to have a negative number of pens? No. So this is going to happen a lot, that you're going to have this x is greater than 0, y is greater than 0. Let's think about that for a second. If we think of our coordinate plane, where in the coordinate plane, do you remember your quadrants, 1, 2, 3, 4? Which quadrant or quadrants is it where x is greater than 0 and y is greater than 0? This one right here. You only need to worry about quadrant 1. In this case, it isn't always true, but it often is that you only have to worry about that first quadrant because you're going to be dealing with positive things. So rather than drawing the whole grid, why don't I just draw this part of the grid here? Why don't I just draw that, since that's all we're really going to be worried about? That's what I'm going to do now. So I am going to draw those axes. Good. And we know that our answer, our feasible region, has to be inside this region. It's not going to come out here or here, because this would be in the negative regions, right? This would be second quadrant, which is negative x value. This would be fourth quadrant, which is negative y value. It has to be inside this first quadrant. So that's good news. Okay, we've already dealt with these two here. Okay, so we only need to graph these two lines up here. So let's start with the top one, x minus y. Now remember, how we're going to graph this is we're actually going to graph with we're going to graph y, x minus y equals negative 4. It is nice to have these in y equals mx plus b form. So let's do that. Let's switch this to y equals mx plus b. So to do that, I want to get the y to be positive, right? I want it to be like this. Y, like positive y, equals mx plus b. So I need the y by itself, and it has to be positive. Do you see? I can just move that y to the other side, and it would become positive. Let's do that. Move that y to the other side. It becomes positive. The x is still left here. And this negative 4, I don't want it over here. I want the y by itself. So why don't I move the negative 4 to the other side, and negative 4 would become plus 4. Great. Y equals x plus 4. And do you see this is slope-intercept form? What's the y-intercept? 4. So I go to 4 and put a dot. And my slope is, what is the slope? 1. Or 1 over 1. So up 1 over 1, up 1 over 1, up 1 over 1, etc., etc. I'm going to draw my line. Should I do a solid line or a dotted line? Well, it's greater than or equal to, so it has to be a solid line. Great. Let's worry about the shading after. Why not? Alright, the next one we're going to graph is 2x plus y, and we're going to graph equals 10. Again, it'd be really easy to switch this into slope-intercept form. Get the y by itself. We want to move the 2x over, so it would become negative 2x, and the 10 is still a positive 10. Okay, y-intercept is 10, and the slope is negative 2 or negative 2 over 1. So we're going to rise negative 2, which means go down 2 over 1, down 2 over 1, down 2 over 1, blah, blah, blah. So we can connect that. Solid line or dotted line? Solid line, because it's equal to. Excellent. Now what I want to do is I want to do the shading. I could have done this before, but I'll just do it now. Here, let's try the test point 0, 0 in both of them and see if it works or not. So in the first one, if you try, so by the way, the first one we drew was this one, right? This line here. And if I try 0, 0, I get 0 take away 0, which is 0, is greater than or equal to negative 4. Is that true, that 0 is greater than or equal to negative 4? Yes, it is. So that means that we need to shade below this line. We're going to shade all down here, right? I'm not going to draw it all yet because I'm going to clean it up after. Okay, if we look at the other one, I'll change colors. If I look at the other one, and if I put 0, 0 in here, I get 0 plus 0 is less than or equal to 10. Is that true? Yes, it does. It is true. So we have to include the 0 point in this line too. So that would be all these ones down here. Now, do you see which region it is that has both shades in it? Which one is the actual solution here? It is this solution, this area down here. So this is actually the only region I'm interested in, is this region down here. So you can do the best shading job you want down here. This is the region that we're interested in. Step 2, find the vertices. Okay, so I look in my shaded region, and I don't have to worry about all the points in here. Thank goodness, that would take an eternity to figure them all out. I only have to worry about this vertice, this vertice, this vertice, and this vertice. That's it. Those are all the 4 vertices of this polygon here. So what are those points? Let's write them down. Well, this one's 0, 0. So sometimes I do it as a table. I'll put like point, and I'll just put value of objective function. You could just put value, but just so you know what I'm talking about, I'll put value of objective function. Okay, so one point is 0, 0. You can do them any order. How about this one next? 1, 2, 3, 4, 5, 0 is another one. What's this one? 1, 2, 3, 4, 0, 4 is another one. And this one is 1, 2, 1, 2, 3, 4, 5, 6. 2, 6 is the 4th one. The maximum and minimum are going to be at these points. Step 3 should be calculate the value of the objective function at each vertex. Well, what is the objective function? Here it is. The objective function is c equals 7x plus 3y. So I'll just write that here, c equals 7x plus 3y, and I'm going to figure out for each of those points what's the value of c when I plug that x and y value into this equation, into this objective function. So in this one it would be c equals 7 times 0 is 0, plus 3 times 0 is 0, it equals 0. This often happens that your origin will be one of your points, and it often will be the minimum. Why? Because basically it means you're not doing anything. Okay, next one. C equals 7 times 5, which is 35, plus 0 times 3 times 0, which is 0, so you get 35. Next one. C equals 7 times 0, which is 0, plus 3 times 4, which is 12, so it equals 12. And the last one, 7 times 2, which is 14, plus 3 times 6, which is 18, which equals 32. Oh, interesting. Do you see that? If this was a pens and pencils example, it actually turned out that it's a better solution not to make any pens, but just to make pencils. So that would be really, 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 really useful to know if you were someone who had a pen and pencil factory, and then you hired a mathematician to do some linear programming, and the mathematician came back to you and said, you know what, if you want to increase your profits, stop making pens, just make pencils. So this is good information to know. The 4th step is just to go through and pick out what's the maximum and what's the minimum. Well, minimum means smallest. This is the minimum value. The minimum value is 0. C can be 0. When is it 0? When x is 0, here's my x, and when y is 0. If x is 0 and y is 0, then c is 0. Not very interesting. What's the maximum? Here's the maximum. The maximum is 35. When do we get the maximum? We get the maximum when x is 5 and y is 0. Minimum, maximum. Done. Alright, we're just going to get the process today of drawing this system of linear inequalities, getting the vertices, and calculating the objective function for each one. And then next day we're going to do the wonderful, you have to figure out the objective function and you have to figure out the constraints from a very lengthy word problem. But if you can get this part down, this will really, really help you, obviously, for next time.